and using them to introduce props, something called prop presentations and proofs. This isn't general proofs. This is a certain kind of proof system that comes from, that we'll talk about, in terms of signal flow graphs. So a signal flow graph, I think these were invented by Claude Shannon. And they come in, I guess what they kind of look like this. You have some things that split wires. You have some things that take two wires and kind of add them together. I don't usually write the plus, but there's a plus there. You can scale things by a number, or you can maybe integrate. So what you're imagining is what you should imagine is on each of these wires is maybe a number, or maybe it's a signal through time. And then you can take these signals or these numbers or whatever kind of thing is on the wires, and you can combine them, or you can split them. And at the end of the day, you kind of have how signals flow from one end to the other of this thing. So instead of using integration, even though that's kind of an important thing that people use this for in control theory, let's just use scalars for right now. So imagine that x and y are numbers that come into this thing. Then what numbers come out, I guess? So let me make it a little tiny bit more complicated. That's a splitter. And I'm going to combine, okay, there we go. So the numbers that come out are, you take x and y, and if you want to know what number is coming out of a wire, you ask all the different paths that you can get there and what the amplification was along that path. So from x, I can get to this guy in a bunch of different ways. I can go like this, and that contributes an x. I could go down and then through the 3, that contributes 3x, and then back up, so that's 4x. And I guess that's the only way for x to work. And from y, I could do just about the same thing. Let's see. I can get a y, I can get 3y, and I can get 5 more y, that's 8y. So why don't you try this one really quick? You can tell me what that is. Yeah. Did I do something wrong? Oh, 9y. But you've already passed the test now. So what's the bottom one from x contribution? Anyone have it?
3.
Okay, 3x, and how many y's?
8.
3x plus 8y? Okay. So this is 4x plus 9y. So that's kind of the very basic sort of signal flow graph with no feedback, just things kind of traveling from left to right. We'll talk about feedback systems later, which come up in control theory. And we'll use this kind of picture where all the wires are unlabeled because they're all carrying the same sort of thing, signals, to introduce something called props. Props are a special kind of monoidal category. So monoidal categories we talked about before, and they have a string diagram, a wiring diagram language that they can interpret, where you can draw pictures like this. And the monoidal category says if you know what this function is, this morphism is, and this morphism is, it can interpret what you mean by this morphism in a unique way. Like in what's called a category, you can interpret strings like that, but you can't interpret parallelism. In a monoidal category, you can interpret parallelisms. A prop is a special kind of monoidal category, so we can interpret wire diagrams like this if they're of a certain special form, which is not exactly this. This is one case of a prop. So we'll talk about free props, which are kind of like Hasse diagrams for props. In other words, they're kind of, you tell me what you want to put in there, and I'll just freely invent this thing. Kind of like if you draw a Hasse diagram or a graph, then you freely create a post set or freely create a metric space. So we'll talk about free props, and we'll talk about presentations of props. I'm just going over right now what we're going to do today. You're not supposed to already understand any of this. Presentations of props, which are kind of generators and relations. And the goal of this isn't just to say what generators and relations for props are, but to kind of say what generators and relations do in general in category theory and throughout math. A way of thinking about very big structures by saying, here's what I need to tell you to completely define the structure. Right? So like for a metric space, if I tell you 3, 4, like this, you can already tell me what the distance from this point to this point is. It has to be 7. It's the minimum thing possible such that it obeys the laws of metric spaces. In the same way, we're going to talk about presentations of props where we give generators and relations for props. And finally, we'll talk about proofs. So I guess graphical proof systems. We'll talk about graphical proof systems. So that's the kind of full story for today. So I want to start by recalling, so I guess that was the introduction 1, and this is 2, introduction to props. So I said before that props are a special kind of monoidal category. And I just want to remind you what a monoidal category is. So we've talked about it before, but we've talked about a lot very fast, so we might as well say again. So recall, a monoidal category. I like to write this in, like what you need to tell me to give me one of these things. You need to tell me a category C, an object of C, and something called a tensor product. Consists of, well, now I say it more clearly, a category C to an object I in ob C, a special object called the unit, and 3, a functor that takes two objects of C and gives you back an object of C. And a functor also will take any 2 morphisms of C and give you back a morphism of C. This is what's going to happen when you take two objects, you're going to put them in parallel. That's the way you think of it. And when you have 2 morphisms like F and G, you put them, you put the morphisms in parallel also. And you get a morphism from the tensor product of the morphisms here and the morphism here to the tensor product of the morphisms here and the morphisms here. So it's like parallelism both in object and in morphism. And then these satisfy some rules. Or really there's structure here. It's not just some rules. So what I mean by that is I tensor little c, if for any C, object C, I tensor C is C. So I is going to be drawn as no wires. And therefore, you won't even see it show up in the diagram because it's just always there. Anywhere you want to see it, there's nothing there. I tensor C is C, but not equals. It's actually isomorphic. And C tensor I is isomorphic to C. And technically speaking, I'm supposed to keep track of those isomorphisms and check this pentagon we drew last time and stuff like that. But we don't. That doesn't tend to matter very much for thinking about it. And finally, A tensor B tensor C is A tensor B tensor C. Okay, so that's what a monoidal category is, and they interpret string diagrams because I can take this morphism and the identity morphism on this wire. So X is an object and Y is an object. This is F from X to AB, say, and G goes from B, Y to Z. And this whole thing goes from X, Y to AZ, and it just kind of runs, you can kind of run straight through it. So this would be F tensor identity on Y composed with identity on A up here, tensor G. But this is hard to look at. It's like, you look at this and your eyes glaze over. Unless you're a computer, then you really love this. You hate this. But for us, we like this, because our visual system is really good. So that's what a monoidal category is. We've talked a lot about monoidal poset. So 2 simplifications. The word orthogonal here is being used in the sense of English, not any kind of literal mathematical thing. So 2 different simplifications you could do. One is the category C is a poset, meaning you don't have lots of morphisms between things. You either have a morphism or you don't. Either A is less than or equal to B or it's not. In a category, generally, I could have lots of different paths from A to B. But here I just say, is there one or not? So we've talked about this, monoidal posets. I forgot another thing. C tensor D is isomorphic to D tensor C.
It's symmetric.
Symmetric. We talked about symmetric monoidal posets already. That's where the morphisms in C are very easy. There either is one or there isn't one, instead of a whole set of them. Here, today, a prop. So this is symmetric monoidal posets, props. Ob C is the natural numbers. I is the natural number 0. And tensor is plus. So it's M tensor n is m plus n. So what if your objects are just the natural numbers? Then you're in a particularly easy situation. And why the natural numbers? Because we know that given any 2, we're supposed to be able to tensor them. So if I just even have one object, I know I'm going to get that object tensor with itself, which means draw it in parallel with itself. So I have I know what this means. It means my generating object. This means I have 2 of them, 3, 4, etc. So over here, I had x and y, whereas over here I just have some number of inputs, some number of outputs. Right. So what am I saying here? What I'm saying is that every wire is the same sort of thing. They're all carrying the same sort of information. All you know about them is how many there are. That's the natural number. Does that make sense?
Yeah.
Okay. Because you could imagine situations where each of these was carrying, this one's carrying flour, and this one's butter, and this one's eggs, right? And then it's not the case that they're all carrying the same sort of thing. Each wire, in order for this wire to connect to this wire, this port to connect to this port, if this one's exporting eggs, this one better be importing eggs. Now they're all just eggs. Everything's eggs flowing around. Okay, so that's what a prop is. A prop is a special kind of monoidal category where there's only one sort of object, but of course you can tensor it with itself, which we call adding. Okay, so I will give examples. Examples. One, mat. So in this thing, it's going to be a prop. Examples of props. So it's a monoidal category. Its objects are the natural numbers. I don't have to tell you that because that's forced by being a prop. But I do have to tell you what the morphisms are between 2 different natural numbers. So what do you think the set of morphisms between m and n in mat should be? Let notation be your guide. The notation, if you have seen this notation before, is that this would say m by n matrices. So it's a set of all.
But how do the matrices act on the natural numbers?
How do they act? So all we need to know is not, we need a hom set, we need a set for every mn, the set of morphisms. They're not actually acting on the
Well, in
elements.
that case, you could use anything. You could use a graph with one edge and two nodes and label one m and one n, put an arrow there. If you
So you say that the set of morphisms from m to n, so let's say n to n, would be you put one little node and you label it with something, and you jam these guys in there and these guys there. And then you need to tell me the composition. So if I have another one of these, what do you want this one to be? Well, maybe you want it to just be that picture again. And then you need to tell me what, that's basically it. So you've basically defined a new prop. It's just a very boring prop. I'm giving you a more interesting prop. But I can't say yours is wrong until, if you are able to give me this stuff, then you will have a prop. That's fine. The rule is you have to tell me what you want to allow in for any m and n. You're telling me what you think are allowed to go in there. And if you say you're allowed to put this sort of thing in, I say great, and then let's say I have this shape and that shape, you have to tell me how do I combine them. And lastly, the part I forgot when I just wrote this diagram, I said that's basically it, I was wrong. If you have this shape and this shape, how do you combine them that way? And if you tell me all that stuff and it satisfies these rules, then you've got a problem. It's just not one with a nice name like Matt. Matt is a nice name. Okay, so it's the set of matrices. I guess you could say, if you let m be the set 1 through m, then you could call this the set of functions from m times n to, say, the reals. So these are like the real valued matrices. But you know what? Mat mn just means m by n matrices. So I have to tell you, I told, sorry, what's your name? I should know. What, Tim?
Tim.
Yeah, sorry about that. I told Tim, I'm required to tell him, he's required to tell me, given an m by n and n by p, what he wants the composition to be. I have to do that too. I have to give, if you give me an m by n matrix and an n by p matrix, I have to tell you what the composition should be. Well, I use normal matrix multiplication, if you know it.
So why didn't you just say that instead of saying it's from the natural numbers, it's from these sets of contiguous natural numbers?
Which contiguous?
What you have for n or m underbar there. I mean, why don't you just use that directly? It makes it clear.
Because they aren't required to be that.
One's just a shorthand for the other, as far as I can see, and just identify with the integers rather than with the set.
But I don't have to, yes, that's true. Yeah, it might.
So why would you say yours rather than David's? Why would you say they're the sets? Like,
because
it's simpler to talk about your
I-
objects being the natural numbers than your objects being sets of contiguous natural numbers.
I regard it as a shorthand for when he wrote out more fully there. That made it much more clear to me.
Okay, we'll see if it keeps working, and if it does, then we could hope that it will always work. In general, though, the objects of a category shouldn't be confused with, like, I mean, we think of them as meaning something, but we
So
only
is
use
this a concrete category, or isn't it?
What do you mean
yes,
by-
I guess so.
The objects have an underlying set structure.
Yes. Okay, so, but the morphisms are not set morphisms of sets. This is not a map from M to N. So I guess it's not a concrete category. Anyway,
No,
he's
but
asking questions from, maybe from a book about concrete categories. But it's okay, we can think about it this way, and if something changes, if we find an example that doesn't use this, we'll. But you're right, we think of them as strings. 1, 2, 3, 4. We think of 4 as this many strings, so I don't see why it should ever cause a problem to think about it this way if you want.
Right, so there we go.
Okay. Oh, I'm supposed to tell you how you multiply matrices, how you compose matrices in series, but I'm also supposed to tell you, given an m by n matrix and M prime by N prime matrix. So I have a 2 by 3 matrix there, and I have a 1 by 2 matrix there.
There's a sense in which this does work. If you just let your objects be maps from that set to the reals or any ring, then they are essentially vectors, and the matrices act on the vectors.
Mm-hmm.
Mm-hmm. Okay. So M plus M prime, N plus N prime. So in order to give someone a prop, you have to tell them what are the morphisms, like what can you draw in a box. You have to tell them how you compose in series. You have to tell them how you compose in parallel. So for this, the way I'm going to compose in parallel, given a 2 by 3 and a, is that called 3 by 2? And a 1 by 2, I'm supposed to give you a 3 by 5. What 3 by 5 matrix should I use?
Like tensor or no.
No, it's the direct sum. Really.
Direct sum.
It's a direct sum, so it's like a block diagonal.
Yeah.
So you have, so let's say this is A, B, C, D, E, F, and X, Y, Z. You go A, B, C, D, E, F, 0, 0, 0, 0, 0. What? Oh, X, Y, Z. Why is there so many?
I don't know why this is.
X, Y. 0, 0.
And if you look at these sets as vectors, then it's also the direct sum of vectors.
Yeah, direct sum of vectors and direct sum of, so this would be called plus. And often we use the plus symbol in a prop. It tends to be the right one. But that's just...
Saying that tensors are multiplication is not commutative, yes.
Okay. So, any questions about that? Okay. Let me give another example. 2 port graphs. Okay, so I'm giving an example of props. So this prop of port graphs, the objects are the natural numbers again. So what is a HOM? Let's call it PG. It's the name of our prop instead of MAT. So what is PG from M to N? Well, the picture is going to be like this. You have M on the left and N on the right. And inside you have some number of boxes. And you have, I don't know, a picture like this, as usual. Some kind of messy thing. So these will be the morphisms from M to N. Yes?
So are these just arbitrary functions from M inputs to N outputs, or is there some more specific structure here?
What do you mean functions?
I mean, these example morphisms you've got, like what's this box?
What is this right here?
Yeah, like what are the constraints?
This
of
is
this
a
graph?
picture. So a picture of a morphism G, taking G in port graph of 4, 5. This is a picture of a morphism in port graph 4, 5. So we could draw another picture of another morphism in port graph 4, 5. There's another morphism in port graph 4, 5.
So just wires going anywhere, boxes with any number of inputs and any number of outputs.
And they're all acyclic, let's say. But to make this more, like these are pictures you could draw. That's all they really are. In fact, these are the pictures that make sense in any prop we'll find soon. But to make this precise, you can say what this is in a way that a computer could understand instead of just pictures, right? So what is it? Well, to do that, you have to get more formal and write things down carefully. And so let's do it. So, so a port graph consists of a V, an in, an out, and a iota, where, one, V is a set, a finite set. I guess we're thinking of them as vertices, but maybe it would have been better to call them boxes. So in this case, the V will be like the set FGHI. So a finite set of vertices. Two, functions in, taking V to the natural numbers, and out, taking V to the natural numbers, that assign to every one of our boxes a set of inputs and a set of outputs. Not a set, a number of inputs and a number of outputs. And three, an isomorphism, or a bijection, a port graph, an MN port graph. So with M inputs and M outputs. It's an isomorphism that says every input has to be connected to, every supply has to feed one demand, and every demand has to feed a supply, be fed by a supply. So here's a demand. F is waiting for input and gets it from there. I is waiting for input and gets it from there, etc. Right? This guy is waiting for input and gets it from there. So these strings are just a picture of an isomorphism. And what the isomorphism is, it's the elements of M defined over here like we did before. So all these are suppliers, and all the outputs of the various vertices, so plus the disjoint union over all vertices of out of V. So for every one of these guys, and for every vertex, and for every output of that vertex, I get a supplier. And that's isomorphic to a set of demanders, which is N plus the disjoint union over all V and V of in V. Can you guys read this? Did I make it too small? It's saying that we have suppliers and we have demanders. And the suppliers are all of these guys together with all the outputs of the boxes. So that's supply, that's supply, that's supply. And all these are supply. They're supplying signal.
But that doesn't uniquely specify how the thing is wired up.
So let's try. I say it does. So let's try. So that's what makes math class different than other classes is
I mean,
whether
you'd have
we can
to
check.
do that pairwise
Right.
on the set of all pairs of vertices
So
in order to get that to work.
okay, so let's try this. So here,
Don't get too complicated.
yeah, don't get too much. A, B, C, D. Oh, sorry. 1, 2, 1, 1, 2, 1, 2, 1, 2, 1, 2, 3. Let's call this V and W. So on the left, I had M plus these the disjoint union over all V and V of the outputs of V, our supply,
Where's that plus there mean?
plus disjoint union.
Oh, okay.
2, iota is the name of the map. 2, N, disjoint union, the disjoint union over all V and V of in V. Okay, so in this case, we have 1 and 2 there, and we have V1 and V2 here, and we have W1 and W2.
But out does not, out the way you defined it is not labeled by the particular V that the out V.
V2, W1, W2. We'll check, we'll get there. Okay, on the output side we have the N, which is the 1, 2, 3, and we have V1, which means this input and we have W1 and W2. So it's, the bad thing about a prop is that it can be a little bit hard to like label things in a nice way, but.
Do we need other stuff to rule out cycles? Do we want
Oh,
rule out
sorry.
cycles?
Yes. Such that no cycles. Thank you.
Which
Okay,
one of
There
those-
has they have to be the same size. Do they have to be the same size?
Same size as well?
Luckily, they're both 6.
I mean the definition.
Which?
In the definition.
There's an isomorphism.
Oh, yeah.
Okay, so this 1 is feeding V's 1. This 2 is feeding what? This 2 means this 2.
W2.
W2, great. Who is feeding the output 1?
P1.
V's 1, yeah. Who's feeding the output 2?
W1.
W1. Who's feeding the output 3? W2. And who is V2 feeding W1? Okay. So we got an isomorphism, and we'll always be able to do that because it's a one-to-one matching between the things that are giving and the things that are requiring.
Okay, I get it.
Okay.
But does that preclude loops or feedback by itself?
No, I should have written it there.
Okay.
I got a little.
You chose a nice
Challenged.
So if someone did this,
Mhm.
where it goes down and back up, that would be the same same wiring diagram. The isomorphism would be the same because this guy eventually goes there, no matter how you drew it, right? So this specifies it in a more kind of clean language, but it's not as nice for the eye to see this isomorphism being drawn as it is to see the wiring diagram, especially if it's a nice wiring diagram. Okay. Any questions? So that's a port graph. It has to be, I didn't say it, but a port graph. So let's say we're looking at acyclic port graphs. Acyclic means no cycles. Okay. Any questions? Yeah.
This is a silly one, but why are they called port graphs? Where we're heading?
We're not heading there.
Okay.
No, because we see graph with labels and with vertices and edges, kind of, and we see ports, which are these little wires sticking out.
Okay, yeah.
So let me say kind of what it means that they're acyclic. I mean, you can already see, but if you take those inner vertices, well, let me make it slightly more complicated. If you take these guys and look at them as vertices, what you see is this, that. Maybe you get to see these guys too.